x Vx dx. So when you integrate 0x, okay, so you have minus 50 times 10 to the power 3x dx. So this will also be equal to minus 25 times 10 to the power 3 x squared. It's the same. Okay. I think some of you have seen this before mathematically. So what this means, okay, I'm now going to sketch my bending moment diagram. Okay, I'm going to sketch our bending moment diagram. So I'm going to bring it lower. So we have our vertical axis. Go on. Good. We have our so I'm going to call this at 50 m as a function of x. We're going to have 50 or m, and this is times 10 to the power 3 Newton meter. Whereas the other one on top is just Newton. Okay, 50, 40, 30, 20, 10, 0, minus 10, minus 20, minus 30. And I'm going to stop there. And then we have okay. So this is our x. Right. And then I'm just going to stretch the green. Okay, so we know exactly where we are. So this is our 0.8, 3.2, 4.0. Okay. So we know by looking at the bending moment diagram or bending moment equation, right? What will happen when m is equal to 0.8? Okay. So when m is at 0.8, right? This will be equal to what? This will be minus 25 times 10 to the power 3 multiplied by 0.8. Okay. So minus 25 power 3 times 0.8 is equal to 20. Hey, no. Is it 25? Yeah, minus 25. I want something 50 minus 25. Yeah, minus 25 power 3 times 0.8 times by 0.8 is equal to minus 25 power 3 times 0.8 times by 8. Oh, is equal to minus 16 times 10 to the power 3. Okay, Newton meter. So we know up to 0.8, we're going to be at 16, which is at this point. And because of the second order polynomial function, minus means set phase. So what you do is you just draw a set phase down here. Okay. Now another way to calculate the bending moment is, just to help you recall, is by looking at the area. This area over there. And if we calculate the area, so we know if half base times height. So this can, so moment, moment at 0.8 is also equal to half. The base of the shear force diagram is 0.8 and minus 40. So this will be equal to 0.5 times 0.8 times by 40. So it's also equal to minus 16 times 10 to the power 3. Okay. So you can see the relationship between shear force and bending moment diagram. Okay. So by taking the area, it is your what moment. Or mathematically, you can just integrate. You also can get the same. The advantage of using this, okay, advantage of using the function forming the equation is that you know how the profile look like, right? If not, it can go either way. It can go this way, right? Or it can go this way. You don't know. Okay, by looking at a function, you know it will go this way. Okay, because it's negative. Negative means set phase, right? So the next thing I'll do another time. Okay, another one. So the next one we are going to look at is we are going to look at between, or not between. I'll do at point A, at point B. Now we have to do at point B because at point B there's a reaction force. Okay, we cannot do B to C because there's a feature that will miss out. So from point B is what we call when x is equal to 0.8 meters. Okay, so again, the datum is still the same. Okay, datum on the left-hand side. But now we fix our distance from here to here, we fix at what? 0.8. And when it's 0.8 over here, now you're going to get constant. So 50 times 10 to the power 3. Okay, 50 times 10 to the power 3 multiplied by 0.8. Hold on. So we know that this is equal to 50 times 10 to the power 3 multiplied by 0.8. Right? So this will be equal to, so 50 power 3 times by 0.8 is equal to 40 times 10 to the power 3. And the distance from here to here we know is equal to 0.4. So we know that this is V at point B. And then we will determine moment at point B. Now at point B, we have a force coming here. And this force is sitting at 120 times 10 to the power 3. Before that, between A and B means less than 0.8. You don't see the what? You don't see the 120 times 10 to the power 3. Now you do see the 120 times 10 to the power 3. So that's where the points where you have to analyze, okay, is where you have change in load. We have to pick point B because there's a reaction at point where? At point B. Okay. So from here, positive is going up. Summation of forces y is equal to 0. So you have minus 40 times 10 to the power 3. You have plus by 120 times 10 to the power 3. Right? And then you have minus V at point B is equal to 0. So V at point B comes to be equal to 80 times 10 to the power 3 Newton. Positive now. Okay. And then when you take moment, you realize there's no difference. Okay, summation of moment Z at point B. So we are taking moment at this point over here. Right? At this point over here. So what that does now, so what we have is equal to 0. So we will have 0.4 multiplied by going anti-clockwise, so 0.4 multiplied by 40 times 10 to the power 3. Then we have minus or plus moment at point B. equal to 0. So therefore, moment at point B will be equal to 40 power 3 times 5.4 minus 16 times 10 to the power 3. So at point B, right, the moment, this is still equal to what? Minus 16 times 10 to the power 3. Right? However, our shear force due to the reaction at point B, right, is going to go up by what? It's going to go up by 80. No, sorry, it's going to be the magnitude is 80 times 10 to the power 3. So now I'm sketching our 80 vertically up. No, I can't see. Sorry. So this will go vertically up. And you will stop at 80. Okay. So you can see at point 8, the 80 going up to 80, there's no area. That's why it stays at minus 16 times 10 to the power 3. Okay. But you have to do this. Okay. If you don't do this, you'll miss out at point B what is going on. Okay. I'll do one more. So between I'll do all the way. Okay. Maybe this is a good refresher's course for all of you in how to construct shear force and bending moment equation. So now we are going to go from point B to point C now. Okay. So I need this diagram, just this diagram. Come on, I just need this diagram. I don't need the graph. Yeah. So next we're going to plot. We're going to form the function between point B, right? Between point B to point C. Yeah, between point B to point C. So now the function, the limits is 0.8 x, and it's going to go to 3.2 meters. Okay. So when we have that, I'm going to sketch the diagram. So now we have a force down here, and this is equal to 120 times 10 to the power 3. And then over here, we still have 50 times 10 to the power 3 x. Okay. And then from here to here is our x over 2. We know the distance from here to here is 0.8. And down here is still our datum. Why the datum is on the left-hand side? Because 0 is always on the what? Left-hand side. Okay, for that reason. And then from here, we are going to have, so this is our x, right? And then this is v as a function of x, moment function of x. Okay. So I can get rid, I don't think I need this diagram anymore. Put it slightly away. So again, same thing, summation about forces in the y direction. So this will get 120 times 10 to the power 3 minus by 50 times 10 to the power 3x, right? Minus b as a function of x, and then the whole thing is equal to 0. So what we have is v as a function of x is equal to what? Is equal to minus 50 plus by 120 times 10 to the power 3. Okay. So now we come to our shear force diagram, right? And what we realize that this thing will be going down with a negative slope. Okay. So the next thing we want to find is at 3.2, what will happen, right? So V, if we substitute V at 3.2, this will be equal to minus 50 times 10 to the power 3 multiplied by 3.2. plus by 120 times 10 to the power 3. Okay. So minus 50 power 3 times by 3.2 plus by 120 power 3 is equal to minus 40 times 10 to the power 3.